Looking at tests for convergence. So if I have the two tests I'm going to talk about here are the integral test and the p-series test. So if I use the integral test to determine whether or not something converges or diverges, it's really helpful. I can also look at the properties of a p-series, and that can help me make those determinations. So for the integral test, it says that I can take the series and take the improper integral of the function, and if the improper integral converges, then so does the series. So that's all this says. So what I'm going to do is I'm going to look at my series. I've got n over n squared plus 1. My function then would just be replacing n with x, and that's not really a step you need to necessarily show. I know that it's positive and continuous. So if I want to apply the integral test and I want to start looking at it, I'm going to take the derivative of it. So then now I have the derivative, and I can understand from the derivative that it is going to be less than 0 for anywhere that x is greater than 1, which means it satisfies the conditions of the integral test. So I need to know that my function is on a steady path. So if I look at this indefinite or improper integral, I'm just going to take the limit as b approaches infinity of it, and I'm going to see that I get infinity. Because the improper integral diverges, so does the series. That one's kind of nice. So you just simple, take your integral, but make sure it meets the basic premises first. A second type of series that is really a simple arithmetic test for convergence or divergence. If it's a p-series, so something where we have 1 over n raised to an exponent, that's a p-series. If we have a harmonic series, that would be if I'm adding 1 into that. So I have p-series and then a harmonic series. What's nice about these is if p is greater than 1, then I can get some convergence information out of here. If p is greater than 1, it converges. If p is between 0 and 1, it diverges. So if my exponent is 2, it converges. If my exponent is 1/2, it diverges. So that's really nice about these. So you just really have to recognize it. So if you look at this and you see theorem 9.11, and I look at this harmonic series, the exponent is 1. Even though it's not written, it's implied to be 1, which would mean it falls into divergence because it's equal to 1. If I look at the second one, my exponent is 2, so it's going to converge. And that's really simple and straightforward for convergent and divergent sequences in series.